So today we are going to discuss about K and how exactly K space works. Now we'll understand that's what is given. Any particular point on a K space contributes to the whole image, and any image in a pixel, any image. This is an image. This is the K space. This is an image. Now any if take one point in the K space, it contributes to the entire image. The same way, in one point in an image is a product of all these K spaces. So any image pixel is derived from the entire K. Now, to understand this, we see how the image is formed. We know that when we keep a human body within a MRI machine, they will have a particular the hydrogen protons within the human body will have particular frequency. Now this is nothing but a precision. Now this is a precision is the rotation of the hydrogen ions protons in its own axis when we keep it in a magnetic field. This is a property of any nucleus where there is hydrogen atom or any other nucleus. There will be particular precision that is happening, and this is fixed throughout. If the magnetic field is fixed, if the magnetic field is uniform throughout, we will have a uniform frequency throughout the body. Now if to measure this, what we do is to measure this frequency that is produced, this magnetic field that is produced by the human body. What we do, we give an RF pulse. We give an RF pulse. Once we give the RF pulse, what it will do, it will flip the magnetic field 90 degrees so that we can measure it. Why all this happens is what I have explained in the previous classes. Now once we give an RF pulse, we can see that the magnetic field the magnetic field of these hydrogen ions have flipped. Now once the RF pulse is removed, the magnetic field will go back in the direction of the magnetic field of the MRI machine. So that's when we cannot measure it. So whenever the magnetic field is in perpendicular, or it is facing the RF transmitter, that's when we can measure it. So this is how we measure. But what exactly happens? Whatever the information that we measure in this RF transmitter is coming from the entire body. Now we get a signal. Now this signal is what? A net magnetic field. We are getting a net magnetic field. So what exactly we are getting? But now this amplitude will not give us any image. To make an image out of this amplitude that we are getting, we do some changes. So first thing is, from the entire body we have to select a slice. From this slice we need to see what is the signal coming from this slice. Once we know that what is the signal coming from this slice, we need to know what is the signals coming from each stripe. Now once we know what is the signal coming from each stripe, we need to know what is the signal coming from each voxel. Now this is how the from all these parts we can make a image out of it. Okay, now if this is how an image is, now to make this image we need to find what is this stripe made up of. To know what is this stripe made up of, we need to know what is each made up of. First thing is, how do you select a slice? As we have discussed earlier, we give a gradient. So a magnetic field by the MRI machine is V0. So we add some magnetic field to it. Now also we subtract some magnetic field from it. So what we get a gradient of magnetic. Here there is maximum magnetic field, here there is minimum magnetic field. So there is a varying magnetic field when we go from head end to the leg end, cranial to caudal. When we go from cranial to caudal, there is a varying magnetic that tell us. When we go from cranial to caudal, the frequency that is produced by within the body, the hydrogen atom, or the magnetic the frequency that is produced by the magnets, that is the hydrogen protons, the frequency is maximum in the caudal end, minimum in the cranial end, and it is in the middle when in the where there is experiencing only B0 magnetic field. Now what happens? Different areas of the body is having different magnetic field. Now if you want to measure this part of the body, if you want to measure the information from this part of the body, what I should do, I should give an RF pulse which is having same frequency as that of F0. If I give an RF pulse which is having same frequency as F0, only this much portion of the body's hydrogen proton will flip in 90 degree, and we can measure that. Now what has happened, when I give a frequency F0 frequency RF pulse, only the part of the body which is having experiencing F0 frequency will be flipped, and we can measure this part of the body. Now the signal that I received now is coming only from this part of the body which is having frequency of F0. Okay, now this is how we get the particular slice. Now once we get a particular slice, is that now out of phase, the amplitude reduces. Why the amplitude reduces? So we know that. So what I do now, after doing the frequency encoding and slice selection, what I did now is that I gave a phase encoding. What I did is a phase encoding. Now what I did, now each stripe in this plot, in this each row in this plot, or each column in this plot, is by giving a RF pulse, by giving a slice selection gradient, and by collecting the echo by giving a frequency encoding. Okay, that's all is there. Now what I do a second row or second column. So what I do now, everything remains same except that I dephase them little bit. Okay, I dephase them little bit. Now I take the third stripe by dephasing them more. Okay, I dephase them more, but I take the third stripe by dephasing them slightly more. So this is how I take multiple stripes by giving them different defacing gradient. Okay, different defacing gradient. This are all of this I have explained in the phase encoding step. Okay, I have explained in the previous lectures. If you don't understand, please go back and see once. Okay, so this will, by giving these multiple defacing gradients, I repeat the same process by giving different defacing gradient. Okay, so this is how I measure the same slice. I take the same slice and I measure it multiple times. The number of times I have to measure this, the number of times I have to measure this depends on the number of slices that I want. Okay, number of slices that I want along the phase encoding direction. So if there is a matrix of 512 into 512 matrix, then what will happen, I have to repeat the entire step into 512 times to finally get 512 lines to be filled in the K space. Okay, so that's how we fill the K space, and this K space is having only amplitude with respect to time, and each line represent each phase encoding step. Okay, there are number of phase encoding step will be same as the number of the pixel that we want to see. Okay, now if we see in this image, we have measured multiple times the same number of times as the phase encoding step. Now if I see the if I do 1D Fourier transformation, what I have got is I have got multiple frequencies at each level. I have got multiple frequencies and its contribution to the amplitude. The same thing is done for each step. So what we have done is we have done Fourier transformation at each level. Okay, I have done a Fourier transformation at each level. Now I know the frequency, each frequency, the amplitude contributed by the each frequencies. Okay, now what I do a Fourier transformation in this direction. I know that these are the amplitudes contributed by one frequencies by applying different phase gradient. Okay, this is one phase gradient, this is second phase gradient, third phase gradient. So these are the multiple phase gradient steps that we know that. Okay, from right to left are the multiple phase gradient steps. So we know that these are the multiple phase gradients that are used to measure these steps. And also we know that this shows the multiple frequencies and their respective contributions of the amplitude. Now what I did the first time, what I did was I did a Fourier transformation using all this amplitude with respect to time and found what are the frequencies that are contributing these amplitudes. Next what I did, now I have amplitude and different frequencies. Now what I did, I do a Fourier transformation along this direction. Now I know that there are different phase gradient steps which are giving these amplitudes, but the frequency that is giving this amplitude is same. So now I can identify what is the difference in the phase gradient that I have applied between the two steps. Now I know that what is the phase gradient that I have given at each level, and I can get an information in which I can get what is the phase gradient that I have given at each step and what is the contribution of the amplitude after giving the phase gradient. Now I know that if I give this much, if this is the phase gradient that I have applied and if this is the information I am getting, now very concentrate well here. Now see this is how we do the 2D Fourier transformation in the second dimension. Now what I get is a plot where there is phase gradient at one level, there is different phase gradient at one level, and there is a different the contribution of the frequencies at each level. Now what exactly we have to understand is that, now see, if I give a phase gradient of this much, okay, now if I give a phase gradient of this much and if I give a second phase gradient of this much, you see this is the amount of the change in the amplitude that we see. This is the amount of the change that we see. So if I go in the opposite direction, again this is the amount of change that we see. So what we have to understand is that as I give greater and greater phase gradient, now the amplitude contributed by the different step will be different. Also we know that each time, so number of times you have to repeat this step is decided by the number of phase gradient step that I have to give. So that is one thing that decides the time, number of times we have to repeat. One more thing that decides the amount of time that we have to do this step is number of the time to repeat. So once I give an RF pulse with a slice selection gradient, I measure an echo with a frequency selection gradient, then I give a second RF pulse with a slice selection gradient, and then I again measure an echo. Okay, so this again, so this is the time to repeat. Okay, this is the time to repeat. So this is one step. Such how many steps is decided by number of phase gradient, so that will give the time of a scan. So first thing is we need to know how many times I have to repeat this, and once I know how many times I have to repeat this, I need to know what is the time for each step that is given by TR. TR is not exactly each step. Each step is nothing but from one RF pulse to the one more RF pulse. So that is the time for the first one. Now next one starts from next RF pulse. So this is what will give us the time for a scan. So whatever the raw data that we got is nothing but the time domain data, or this is nothing but the data which after Fourier transformation we have uh, got the image formation. We have made an image formation. Now if you see this, first I gave an RF pulse with a slice selection gradient. I gave a phase gradient. I measure a pulse. Now whatever I measure, I plot it here. Now as we have seen in frequency encoding, the frequency will be rising first and then falling down, because we don't give directly a frequency encoding. What we do, we give a frequency encoding in opposite direction, then I give a frequency encoding in the opposite direction, so that whenever I give the frequency encoding, whenever I encode any part with a frequency encoding, what will happen? Now they will undergo dephasing. They will undergo dephasing, and there will be loss of signal. To avoid this loss of signal, I have given a reverse signal first. So what will happen now? Now there is a dephasing happening here. Now when I give the actual frequency encoding, they will all undergo rephasing. So the signal will improve and then again it will fall down, and that's how we measure the signal. Now this is what you have to understand, that as I go to the middle of the K space, the signal is maximum, because that's where the maximum, the all the protons will be having in sync, so there will be maximum signal. So that's why if you see from right to left, it is always in the middle there is maximum amplitude. Or is the one thing that we have to understand, in a K space, if we go from one end to other end, it is the center of the K space that is having the maximum amplitude. Also, if you see in this image, I have shown that if I go from top to bottom, again in the center there is maximum amplitude. Now again this is explained, this is explained by one more image. So what exactly uh, than this is the first phase gradient, this is the second, third, fourth, fifth, sixth. As I come to the middle, you see, as I come to the middle of the K space, the frequency, the phase encoding is least, the phase gradient is least. So what will happen? We'll have the maximum gradient. Whenever we give a phase any gradient, there is loss of sync. So whenever there is loss of sync, so there is loss of energy, so there is so a lot of loss of amplitude. So in the the first phase gradient, the phase encoding gradient, there was maximum loss of energy. So as I go to more and more towards the middle of the K space, the energy loss was less. Now again, as I go towards the periphery, now there is more gradient, so there is more loss of energy. So what it tells is, when I go to the center of the K space along the phase encoding direction, or then again there will be maximum amplitude in the center. Same way in the frequency encoding direction, also maximum amplitude in the center. So this is how we get an image in which there will be maximum amplitude is in the center. But also understand that there is one more interesting, so this is what it's shown as maximum amplitude in the center, minimum in the periphery. One more thing that we have to understand is that, see in this image, now if you see, if you compare 2 points, if you come, okay, I'll give one of, okay, this image is better. If I compare this point with respect to this point, see that there is maximum difference in the phase, so there is maximum change. Okay, it will show maximum change. So the periphery is showing maximum change. So as I go towards the middle of the K space, see the difference in their frequencies is very less. Difference in their phase is very less. Now this is because I am giving minimum phase gradient there. So what it tells us, now the difference between 2 points, the difference between 2 points is maximum in the periphery of the K space. Okay, difference between 2 points is maximum in the periphery of the K space. So as I go to the center of the K space, the difference between 2 points is less. So what will happen? If I want to discriminate between 2 points, okay, if I want to discriminate between 2 points, we have to use the peripheral part of K space. So this is very important principle. So what we have to understand by this image is that the center of the K space is having a maximum amplitude, the peripheral of the K space is having maximum phase difference. So what will be happening? Because of this maximum amplitude, the contrast in any image is decided by the center of the K space, whereas the 2 point discrimination or the edge enhancement, okay, is decided by the peripheral part of the K space. So the periphery of the K space gives us a better resolution, whereas the contrast resolution, better 2 point discrimination or the edge resolution is better in the periphery, whereas the contrast is better in the center of the K space. What we have studied in this. Okay, so what we have seen is the periphery gives better spatial resolution, central gives better contrast resolution. Okay, now if I see this image, this is how a spine image will look with a complete case space. Now imagine if we remove the center of the case space, we can see the spatial resolution is intact. But what has happened? There is no contrast. When you remove the central post portion, there is loss. The same thing, if I only keep the central portion, we get only the contrast resolution, but the edge definition or the spatial peripheral we lose the resolution. If we remove the center, lose the contrast resolution. So this is how a case space works. Now, what are the ways how we can use a case space for? Now, we can use the case space for accelerating a scan time. So what I can do, so this is a rectangular field of, for example, we take only we fill only the middle of the case space, we leave the periphery. Okay, we leave the periphery, but again we know the periphery is responsible for the spatial resolution. So what will happen? Now there is less spatial resolution but a good contrast resolution we get. So whenever we want to see contrast resolution, we can do that. We can remove the peripheral part, we can use only the center case space. Or we can do something called as partial Fourier transformation. Partial Fourier transformation is nothing but we take half, we fill half of the case space, and we will just copy paste the rest half of the case space by using the conjugate symmetry method. So we fill rest of the case space. So this will again, but the image quality will be slightly reduced. So this is how a case space works. A case space is nothing but it is a time amplitude domain when we measure image. So this case space is filled by taking multiple echoes with the different phase gradient frequencies, and then we are plotting with respect to time and amplitude at each phase gradient, and that's how we fill uh, the entire case space of time amplitude domain. And by using this time amplitude domain, we measure, by using this we can reduce the scan time by using this property of the case space. So that is about the case space. I hope you understood. So if you have not understood, please go back and see my previous videos on the MRI basics, and I have explained how to select a slice, how to select a gradient, how to select a frequency gradient, how to select phase encoding gradient. So based on this, I had to explain the case space, but I also tried to include slice selection, the phase gradient and the frequency gradient in this section. But that alone itself, they are separate topics. So please go back and see those videos either from radiorai.in, or you can contact me. I can take classes again if you are interested. Thank you everyone for the patience listening.